Hello, I'm Albert Yu from Purdue University. Today I'll be presenting our work with Donghang Lu, Aniket Kate, and Hamanta K. Maji, titled Polymath, Low Latency MPC via Secure Polynomial Evaluations and its Applications. With the rise of many data processing applications, such as machine learning algorithms like decision tree evaluations, the problem of data privacy began getting more and more attention as well. How can we protect the privacy of user data while still being able to perform useful computations on them? One way this can be done is through secure multi-party computation, also known as MPC. By representing these functions as either Boolean or arithmetic circuits, MPC offer a way to securely evaluate these circuits without revealing any additional information on the user's private inputs. There are many different MPC protocols and frameworks, such as Yau's garbled circuit, Speeds by Demgar et al., and Honey Badger MPC by Liu et al. One way this is done is through the use of secret sharing schemes. In a secret sharing scheme, a party with a secret X can generate several secret shares of X, typically represented with square brackets, and subscript when representing two specific shares. Then distribute these secret shares to various parties, such that when the parties come together, they can collaboratively use their shares to reconstruct the original secret, but learn no additional information on the original secret otherwise. One simple example of a secret sharing scheme is the additive secret sharing scheme depicted here, where the secret shares add up to the original secret. A special type of secret sharing scheme is called linear secret sharing scheme. What makes linear secret sharing schemes especially desirable is that linear operations can be done locally and without any communication between parties. For example, to add up two secret shared values x and y, each party simply needs to locally add up their shares of x with their shares of y to obtain their shares of x plus y. Similarly, to multiply a public value a with a secret shared value x, depicted in this presentation using blue asterisks, each party simply needs to locally multiply the public value with their shares. All that remains is to multiply two secret shared values. This is typically done using beaver multiplication or beaver triples. In order to multiply two secret shared values, the parties will utilize pre-computed secret shares of a random value A, shares of a random value B, as well as shares of A, B. By computing x minus A and y minus B, then opening or reconstructing those values, the parties can obtain the secret share of product x, y using that formula shown above. Note that these multiplications between two secret shared values will be represented using red asterisks. This can be done in one round, as opening a value requires communication between parties. Although we are opening two values, since they do not depend on each other and can be done in parallel, they belong in the same round. Mohaso and Zhang also generalized the beaver multiplication technique into the realm of matrices. Instead of performing operations on each element individually, they directly generate beaver triple-like matrices, that being random matrix A, B, and AB. This allows them to directly perform multiplication between two matrices. While these generic MPCs are now complete, as we have demonstrated how to evaluate an arithmetic circuit securely, they often have prohibitively high costs. On the other hand, application-specific MPCs may be too narrow. Ideally, what we want to do is identify common building blocks prevalent throughout many MPC applications and develop efficient versions of them. With the current advance in computing technology, MPC applications are often bottlenecked on the round complexity. Therefore, ideally, we want to optimize the round complexity of these protocols. That brings us to our contribution, Polymath. The first part of Polymath concerns evaluation of polynomials on integers. In first protocol we developed generalizes beaver multiplication into product of three secret shared values. To do this, we utilized pre-generated shares of a random A, B, C, and shares of A, B, C. Then, by using techniques similar to beaver multiplication, we can achieve the product of XYZ in one round, whereas a direct application of beaver multiplication would have to be done sequentially and result in 2 rounds. However, what we soon realized is that this technique does not scale beyond 3 variables. Therefore, we developed a separate protocol for evaluating a multivariate polynomial term. In this setting, our input are n secret shared values, x1 to xn, as well as n public exponents, e1 to en. And the desired output is the secret share of x1 to the e1 times x2 to the e2 all the way to xn to the en. To do this, we pre-generate secret shares of n random values, as well as secret shares of their inverses raised to the respective EIs. In the first step, we multiply each xi with Ri. Then we open those values. By opening these values, it allows us to perform some of the heavier computations, such as raising to the power of EIs, as well as multiplying them all together in the clear, and require no communication between parties. Finally, we need to multiply by the secret share of the product of all the R's inverses in order to remove all the random values and obtain our final product. This allows us to perform this in 2 rounds instead of big O of log E plus log N round. Note that this is especially significant because 2 is constant and independent of the actual values of n or the EIs. The second part of Polymath consists of protocols related to the polynomial evaluations of matrices. First protocol, developed by Bar, Ian, and Beaver, is used to multiply an arbitrary number of matrices. Inputs are n secret shared matrices, x1 through xn, and the output is the secret share of the product of all these matrices. To do this, we pre-compute secret shares of n plus 1 random matrices, R0 through Rn, as well as their inverses. In the first step, we compute the secret share of Ri minus 1 xi Ri inverse and open all of these values. When we multiply these values together, we can see that the Ri through Rn minus 1 in the middle telescopes and cancels each other out. Finally, we have to multiply by R0 inverse from the left and Rn inverse from the right to cancel out the last remaining random matrices to obtain our final product. This can be done in 4 rounds instead of log n rounds. What we then did is optimize the above protocol for the special case of computing powers of a square matrix. Instead of using n plus 1 random matrices, we only use one random matrix R and its inverse. And by following a similar protocol as the previous one, we can quickly and efficiently calculate the powers of a square matrix, done in 4 rounds instead of log E rounds. To demonstrate our protocols, we picked a couple applications and benchmarked them. The application we've chosen is privacy-preserving decision tree evaluation. Giacomelli et al. Presented a way to reduce decision tree evaluation to comparison and polynomial evaluation. We first assign each non-leaf node with a variable xi. Then each leaf node would be a polynomial with terms in the form of xi minus 1 or xi plus 1. If the leaf node took a left branch at non-leaf node xi, then it will have a term xi minus 1. If it took the right branch, it will have xi plus 1. Then, when we want to evaluate the decision tree, we would assign the variable xi with -1 if the left branch is chosen, and give it +1 if the right branch is chosen. What this does is it allows all but one polynomial to evaluate to 0. In a specific example, suppose that the left branch is chosen at non-leaf node x1, the right branch is chosen at x2 and x3. What we can see is that all of the red terms will evaluate to 0, and only the blue polynomial will evaluate to a non-zero value, identifying it as the correct leaf node. Once we have this way of reducing a decision tree evaluation to comparison and polynomial evaluation, we can use our protocol to perform the polynomial evaluation securely, as well as use a secure comparison protocol to do the non-leaf node comparisons securely. We implemented this onto the Honey Badger MPC framework and ran it for the nursery dataset and obtained some benchmarking numbers. What we discovered is that the time for polynomial evaluation is extremely fast and typically only take up around 10% of the total time. In conclusion, MPC, or Secure Multi-Party Computation, helps to achieve privacy in various applications. While generic protocols exist, we want to optimize some common building blocks. To that end, we present protocols for polynomials and polynomials of matrices that optimize the communication around complexities. Thank you.